So hello, everybody. I'm Mircea. I work, obviously, for Intel. And I'm going to be talking once again about debugging shaders on Intel GPUs. This talk is called Debugging Shaders on Intel GPUs Past and Present because I held a talk last year at a Cauldron in Prague, and I presented you, like, say, the first iteration of the debugging solution for our GPUs. Things evolved, 1 year passed. Let's see where we are now. I'm going to jump right in with a brief description of the graphics architecture and of the execution models and of the available APIs before diving in to debug-specific topics. So from a hardware perspective, the lowest building block is, of course, a thread. Hardware thread, which has a number of registers available. The registers are grouped into two so-called register files. First one called the general register file, large number of registers, each register 32-byte wide. And the second group of registers, the architecture register file, which vary from generation to generation of the GPU. Things like the program counter, accumulators, they vary in number from generation to generation, predicate registers, and so on. More threads are being grouped into an execution unit, into an SMT-like model. The execution unit is the one actually possessing the ALUs and everything required for actual computation, functional units, SIMD, branch control, and, of course, memory access. Going up in the hierarchy, more execution units are being grouped into a subslice. The subslice is a collection of EUs which share, most importantly, level 1 and level 2 caches, and a software thread dispatcher as well. And the top unit would be the slice, grouping of one or more subslices, which basically share fixed function unit and the last level cache, the L3 cache. The fixed function units are units that actually perform quite complex geometrical and shader operations. Advantages of having graphics integrated on your processor. First of all, quite obvious, you have shared physical memory. And starting from the 5th generation of core processors, you also get pointer sharing, so shared virtual memory, right? About the instruction set architecture, it's composed of 32-byte wide instructions. Also, there's the option of having some so-called compacted instructions, which are 16-byte wide. You have SIMD control flow all the way, so one program, one PC per SIMD lane. And you can have predication for every single instruction. So that means you could enable or disable individual SIMD lanes. And probably one of the most important advantages of the architecture is that it's pretty much fully documented, up to and including the 6th generation Intel Core processors. So you have the programmer's reference manuals available, which also document the instruction set architecture, and especially they do so also for the memory access instructions, which are quite complex in this scenario. There was a question last year, how do we learn about the ISA? How do we learn how to write assembler? How do we know how to write code generation, right? How to write a compiler backend for this architecture, where this is the document that you need. So up to and including codename Skylake. And of course, some additional documents for developers and APIs. What is supported from an API perspective? Pretty much everything that's currently relevant. Standard stuff like OpenMP, OpenCL, OpenGL with compute extensions, DirectX. The Intel Silk Plus model as well, and the new kid on the block, the Vulkan API. which is supported by the Mircea driver in the open source world. You see that I'm not limiting it only to compute shaders. Last year, this was just about compute. Now it's a compute and 3D. So this is pretty much the environment, the hardware and the software world, right? This is what you can use to run stuff. Let's see how debugging looks like. Well, first, let's further some example of Silk Plus. So Silk Plus is a proprietary extension, a proprietary model available in Parallel Studio XE and System Studio 2017, providing you with easy pragmas for and APIs for offloading code to GPUs and to other accelerators like Xeon Phi. Just to understand a bit the audience, how many people here use offloading or are into offloading or HPC of any kind? Okay, good. Well, so we offer two models, one synchronous and one asynchronous. For a vector multiplication, you would just have to convert a normal for loop into a so-called circle for loop and have a pragma before it that specifies, well, I'm targeting the GPU, and this is the data that I'm working on inside the loop, and this is the size of the array. And then it's just normal C code. This will be synchronous in the sense that submission and waiting for completion is done automatically by the runtime for you. You have an asynchronous model as well, where you explicitly control the declaration of the shaders, so the offload units, and their submission. So the thing turns now into a function that says, well, we declare it as a graphics kernel that is to be offloaded. The Silk for construct stays, but the submission is different. There's no explicit pragma. There's an explicit declaration that says, well, we use a certain pointer and a certain size for the GPU. We add it to the device queue with a certain name and the input data, and then we wait for the completion of that particular shader or task in this context. So both words available. Now, we're ready for the debugging. So what's new from what I presented last year? First and foremost, for a lot of users, Microsoft Windows support. The solution that I presented last year was Linux only. Last year, I have also shown that some of our components in the debugging stack were closed source. We had a user space daemon for some IP reasons that was actually communicating with the hardware, and it had to be binary only, and that was, let's say, suboptimal. Now, every single thing in the debugger stack is fully open source. That means a debugger library, a so-called interchange library. So we're going to see on the next slides what they're actually all about. The kernel mode driver for Linux that actually replaces that ugly binary user space daemon, dev-mem-based, as stated here. And this has a nice implication on the user end, because you'd no longer have to have a specially configured Linux kernel to allow you to have all sorts of memory access that are required to this character device on Linux. So you can simply have your stock Ubuntu kernel or stock Fedora kernel, and you can use our driver, and you're done. So you don't have to recompile the kernel. And of course, a kernel mode driver for Windows as well. Beside the fact that we have now Windows and everything open source, we have a new architecture, or a reworked architecture of the whole debugging stack, and this is going to be presented on the next slide. Because of one simple reason, the original architecture was highly focused in its, well, as the first iteration, on the primary usage model, which was Intel Silk Plus and OpenCL, with specific runtime runtime library configurations. And these scenarios imply a two-step approach when it comes to generating the binary code that actually runs on the GPU. They implied an intermediary ISA and a JIT compiler. So the architecture was strongly coupled with this particular model. Now, other runtime scenarios and other APIs or runtime libraries do not have a two-step approach. You have like the Mircea driver for OpenGL on Linux. And our driver there simply takes GLSL and compiles it directly to the so-called Gen ISA, so the real binary that can run on the EU. The Beignet runtime for OpenCL as well, the same thing, doesn't use an intermediary ISA. It compiles directly to Gen ISA, so there is absolutely no JIT compiler involved. So we had to adapt also to this scenario. And then one new feature, and this is why I stated on this slide, well, it's no longer just compute, it's 3D as well, is the fact that we support debugging 3D shaders. If you're a driver developer and want to optimize your driver for specific workloads in the gaming world, for example, you might find this quite interesting. So it's 3D and compute now. So this is a breakdown of the architecture that I pretty much presented last year. The debugger components, the components of the debugger stack are the ones in yellow. And in blue, you have the normal runtime entities. So normally, you have, like for the Silk Plus case, you have your host app running on x86. On the CPU, it calls into an offload library, which calls into a JIT compiler that generates the final binary. This offload library will then use some user mode driver, which will communicate with the kernel driver, the i915 on Linux, or a so-called kernel mode driver on Windows. And they will submit the shader, the computational kernel, to the hardware. Now, on the old architecture, all these components were communicating with interchange library. You can imagine that for a normal debugging scenario that would be helpful to the user, you need some debug info generation in this space. They were sending all the relevant data to a so-called interchange library, which is part of the debugger stack. But this interchange library wasn't really smart. It wasn't really active about debugging information. Because, well, the usage model mainly focused on this kind of a scenario, right? So it was passing debug information-related stuff to a so-called debugger library that was being used by the debugger agent, in this case, well, the GDB server. And a lot of debug info-related magic was happening in this debugger library, so inside the debugger process. This red arrow here means that we were doing a lot of inter-process communication, so between, let's say, the inferior process and the debugger. This is the daemon I've been talking about, so this was also some IPC here. This was running as root, dropping privileges, and then using the dev-mem character device to interact with the hardware. And yeah, of course, the GDB controlling the target agent. So what changed? And the current approach is the following. You still have communication at every single level with this so-called interchange library that we deliver. Note that none of these components is directly linked against it. So it's all DL open, DL close, DL sim at runtime level. But right now, the interchange library abstracts the generation of debugging information from the target agent process. So right now, the debugger does no longer care like how that debug information is being generated. Every single runtime should take care of its debug info, right? The debug info has just to be there, or if it's not, you're just left with assembly level debugging. This is because in a lot of these scenarios that I've mentioned before, like Mircea and Beignet, you no longer have this piece here. So you have like some library or some runtime, or now no library at all, that simply communicates directly with the driver. So if you're running an OpenGL application or an OpenCL with Beignet, your debugger will do CL calls directly to Beignet or GL calls directly to Mircea. So these two components are gone. And it's up to this block here to generate proper debug information. And because we want to get rid of the IPC and have some proper accounting of what's happening and who's debugging what, the IPC was dropped because, well, the daemon was dropped. And now you have like a direct communication between the two libraries, one used by the debugger, one used by the inferior, with this entity called the debug driver, which is consistent which is a kernel mode driver on both Linux and Windows. And being a real Ring 0 kernel driver, it ensures for proper security and accounting and rights management and whatnot. The good thing is that, as mentioned, we now have the interchange library taking care of the debug info, and the debugger does no longer care about it. So the debugger just expects it to be there. Some details about this architecture. First thing, in CPU-based debugging, when you have the OS providing you ptrace and providing you security and access rights and whatnot, it's easy to pinpoint, to select a certain inferior to debug, right? You attach to a certain process ID because the process ID is a natural building block of current operating systems, right? Well, there's no such thing as a process ID when it comes to shaders because every single vendor is implementing shader submission and shader management and runtime and scheduling in his own driver. So things are not really standard, at least in the Linux world. Even the first level libraries aren't really standard because you have libdrm for every single vendor. So the problem is, you know that you have an application which submits some shaders and you want to debug those shaders. How could you tell the debugger, well, this is what I want to debug and not something else, because you might have a multi-user system where 10 people submit shaders. And one does OpenGL, one does OpenCL, the other one does Vulkan. So we introduced the concept of a so-called session ID, which is a pseudo process ID, which uniquely identifies, well, one debugging session, right? I might have multiple host apps submitting shaders, and I could do shader debugging with one single target agent, with one single GDB server, one single GDB, for these multiple host apps. The idea is, like, if you're doing heterogeneous debugging, you could use the PID of the host app, assuming you start your debugger after, of course, the host app is started. Or if you're doing things manually, you can user control. You can have full control of it and override this session ID and specify whatever you want. This leads to a so-called client-server model, like at driver level, where the server is actually the debugger, the target agent, that can handle these multiple shaders. And the clients are the host apps submitting shaders to the GPU. The problem is you have to be able to differentiate between different shaders, right? Like on the CPU world, you have process IDs and thread IDs and whatnot. And of course, binary file paths, right? In order to know what debug info to load and to know in the debugger inside which kind of process you're at, you need some kind of identification, and this is why we introduced a pseudo shader ID. So every single runtime is responsible for generating such a pseudo unique shader ID before it submits the shader to the GPU and before it notifies the debugger of the existence of this and the future submission of this shader. Now, a number of questions arise on the client side. So imagine you're writing a runtime library, right? The new OpenCL runtime one, or new OpenGL, or let's say the Vulkan one, right? First thing, if you want to support debugging because you have the compiler embedded, is like, well, how do I know that the shaders that I'm about to submit, if they're going to be debugged or not, right? Because you want to know that at that point. Whom shall I ask? Who can provide me this information? And this is this library over here, which provides a very simple routine, like say, well, is the debugger active or not? And that library knows everything about session IDs and whatnot, and does the proper checks. So that's the clear way to solve this. Now, the second step is, let's say, oh, if I'm a runtime library and I know that the shaders that I'm going to submit will be debugged, the question comes up, OK, what do I do now? What's the requirement? So first thing that you probably want to do is to disable optimization, right? Because you don't want to debug optimized code. And it would also be nice if you would emit some dwarf, probably to the disk, so that it's accessible to the debugger. And then, as already mentioned, you have to assign this pseudo-unique shader ID to notify the driver, basically. So doing ioctls to the driver. That, well, this is the shader with this ID, with this binary, and with this binary size. Because what's going to happen normally, some shader is going to hit a breakpoint, and you want to take care of the hardware in the sense that you don't leave it in a hanged state if there's, say, a rogue submission. So no debugging, but still debugging features activated. So what the debug driver also does is does auto-resuming of shaders of which it's not aware of. So the debug driver will only communicate with the upper layers if the shader that stopped is known to the driver. So this is why the notification via these ioctls is paramount. Is a required thing from the client side. So this being said, was the GDB side of things. Nothing changed there a lot. So we need a new ELF machine type for the GPU. That's a clear requirement. The port itself is completely decoupled from the host side. So you do it only for the GPU end. The XML descriptors contain, for the supported generations, both the ARF and GRF definitions. The generations supported are from the 4th to the 7th generation of processors. So that would be from code names from Haswell to Kaby Lake. That was released last week. And for this task, there were no new GDB commands being introduced. One limitation, for now, it's only supporting the stop the world synchronous model, and the current implementation has no, let's say, GDB native, so it's only a purely GDB server-based remote implementation. Some challenges. The memory model of a GPU is not flat. It is a highly segmented memory model. It means most addresses with which the GPU deals are relative to some kind of a base address. So you need to encode, well, the solution that we chose is to encode the memory type in the upper bits of an address. And that worked so fine so far. Another thing, GPUs have at least nowadays at least 150 threads, up to I think 400 or more. The problem is from a user perspective, how to handle so many threads, how to make sense out of such an offload scenario. And this is where the IT set patch will probably come in handy when it's going to be merged. So I'm really looking forward to that. We needed an extra operator at dwarf level, at debug info level, because we weren't really able to express some of the locations with existing dwarf expressions. But this is also currently under further analysis. And one thing that's quite interesting is that the compiler can treat the general register file, so this big chunk of memory, 128 registers, each 32 byte wide, as both register and memory space. So you might get, in some cases, structs mapped directly in this space, like it would be memory. Requirements and limitations. The list shrinked from last year because of, well, the improvements already mentioned. But still, there's no local debugging, so GDB server and GDB on the same machine if the local desktop composition is activated. That means under normal Windows operation, you have WDDM, I think that's the name thereof, and you cannot do it. What you can do is have a remote desktop, a session with the target, and then you can have the GDB on a host machine, and then basically what will happen is even over RDP, your screen will freeze. Thus, RDP session will freeze. This is also the case with Linux with accelerated desktop compositors like GNOME 3, if I recall well. But there's a workaround for that. You can disable hardware acceleration of the compositor. You can use software rendering, and then you can just use it. On the GDB end of things, we still don't have any backtrace support. So, summing up, the architecture got a major rework. All the components are now open source. We have Microsoft Windows support. We have support for 3D shaders, not just compute ones, and a number of runtimes that were enabled in the meantime, and some more will come in the future. So yeah, this concludes my talk. If you have any questions. I had it last year. It's the same thing. I mean, from a user perspective, nothing really changed. I mean, the same commands.
Yeah, I wasn't in the talk last
Sorry.
year.
Well, it's on YouTube, so.
Nothing changes for you again this year.
Yeah. Well, I mean, the installation is different now. You get DKMS, Deb, or RPM, which nicely installs the driver, and it compiles the thing.
So I'm curious on something. Probably the answer is watching last year's presentation. But when debugging offloading,
yeah,
you have the host side and the offloaded part. If I understood correctly, this is solution for debugging just the offload.
Yes, exactly. We don't mix the two worlds. So there is a solution, a proprietary one, which takes things at the next level, either with Visual Studio or with Eclipse, and then you can do the so-called heterogeneous debugging. But that's a more complex scenario, and this is pretty much out of scope of this talk.
So basically launches two debuggers,
yeah.
front end for both?
Yeah.
You didn't look into making GDB for both?
Oh. That's a longer story. We had the discussion last year, and I still have it on my list, but I didn't get any time approved to actually work on that.
Workaround, it would be possible to have two GDB sessions, one for
it is working. It's part of the product, so it's validated, it's working, and it's quite a nice experience. The problem is you still get at least 150 threads in Eclipse, and oh yeah, of course. If you can do it with Eclipse, you can do it as well. I mean, you get your IA side stuck in an ioctl, waiting for the completion of the shader, and then you can. Yeah, and this is what I was mentioning about the session IDs, because, for example, at this thing here, at that point when you're stuck into the ioctl, you already know the process ID of your inferior, and then it gets really easy to do the stuff. Please.
I was thinking about how you're having to implement this custom kernel driver because of essentially limitations in the scheduler.
Which scheduler?
Well, so the GPU scheduler, you're talking about the new shader IDs that map to
Yeah.
IDs. So I wonder if there's a possibility of modifying ptrace.
Yes, that's.
Have hooks into the kernel mode setting driver that allows the kernel mode setting driver to notify ptrace of when it's scheduled a new ID.
Yes, but considering the current architecture, this doesn't really make a lot of sense because we're completely bypassing ptrace. So these calls here are just normal ioctls, right, that we define.
For this implementation, but so a colleague of mine worked on a debugger similar to this
Okay.
on the vendor, and they had a completely different debug server implementation. So it seems like we're kind of fragmenting this when we could go through ptrace. And obviously, this is hard work to do. You've got to modify the Linux kernel pretty seriously to do that. I wonder if you think there's any value in doing that, and also if it's possible.
Well, there are two things. First of all, you said that, well, it means modifying the Linux kernel. That's not 100% correct. You're not modifying the kernel itself. We are not touching any single, with this driver, we're not touching any single line of code from the Linux tree.
In his alternative model.
Oh, okay. Well, in that, well.
It would be a caveat that you would have to do.
Yeah, the nice thing here is that this debug driver and the normal graphics driver, they're completely independent. And this one is quite unaware of this one. So from that point of view, it's quite easy. Well, let me ask the second question, and then the question was like, would it be feasible to have ptrace, or would it be imaginable? Well, I mean, I can clearly imagine this as a ptrace extension where you have like a very generic mechanism of saying, oh, ptrace, enumerate the offload devices, and then enumerate the extensions available. Like you have like the DRM ioctls, right? They are defined for every single vendor and kernel mode driver. And yeah, that would be completely doable. But you have to have someone starting this standardization process and steering this in a politically correct way where all the vendors are happy with it. And that would also mean, and this probably is also more a political or a management question, that you would need support in the mainline kernel for the functionality that those ptrace extensions are going to use. So this has some very deep implications. Of course, it's doable, right? I mean,
well, I guess it's pushing a technical problem into a political one. I don't know which I prefer to tackle.
Yeah, I mean, like let's put it like this: the current approach, this one, the new one, is quite user-friendly. It's fully open source, and it's also quite easy to use to some extent from installation and whatnot. It's quite transparent, and you don't need a lot of consensus to implement it, right? As long as you play by the rules, it's doable.
Yeah, so maybe sort of just to follow up on this suggestion, one reason I see why it might bring benefits is if you want to implement this full-blown heterogeneous debugging solution within the existing GDB infrastructure, because the existing GDB infrastructure, as we have done, for example, on the SPU, we support heterogeneous multi-architecture debugging in GDB, but we don't support multi-target debugging. that means that the heterogeneous debugging only works if so the interface to the process is shared for both the architectures.
Oh, okay.
So you have to have a single ptrace interface to one process, and that process can then use different architectures, but it has to be one ptrace interface to one process.
Well, then there comes the question, like along the lines of modifying ptrace to support this action. How hard would it be to actually get rid of this limitation in which you actually support multiple targets without having the limitation that you have to go to the same interface? So that's also a question worth asking, right? Because that's a current limitation of GDB.
Right. So, but the point is, if you had structured your interface so that it would satisfy that requirement, then you could use the GDB.
True, but as said, structuring that interface in that manner has very, very wide implications here and at the generic Linux kernel level, and that's a battle you have to fight. That's a strong one.
So does it make sense that ptrace is very process-centric? Like every ptrace call needs to be targeted to a process.
Yeah.
Through that PID. Does that make sense in this?
Yes, it does, and this is why I emphasized the concept of this session ID and said that, well, it can be the PID in the scenario that you mentioned, for example, like. Yeah, because there's always these shaders don't come to life by themselves, right? They're always compiled by some runtime library and submitted by a host app. So they are being owned by the host app. They are not orphans from a whole system perspective, right? But that would imply probably, I'm not 100% sure, but I would strongly assume that would imply adding some more let's say, bookkeeping logic at the driver level. But it's something certainly doable, and from a ptrace perspective, it fully makes sense. You could probably enumerate the list of shaders that are on the fly, the ones that are stopped, because you also have to consider one thing, and you mentioned scheduling. Modern GPUs nowadays have very, very complex scheduling mechanisms. They have basically their own hardware scheduler. So things are starting to be really, really complex. It's, you basically have, well, an OS within an OS from that perspective. And that's getting harder and harder to work with. Please.
You said that all the components are open source.
Yeah.
Where are they? I'm mainly interested in the parts that deal with the huge multitudes of threads and different address spaces and things like that.
As part of these packages, the sources are delivered with them, so you download the beta, the test version, the evaluation version of one of these two, and you get the tarballs inside, along with pre-built binaries. But all the sources are there. So GDB, so you get two tarballs, one like GDB containing this stuff, and another tarball containing the other three components.
How stable are the interfaces? I assume that the kernel interface is not stable. The library.
Sorry, yeah, true, correct, good point. The interface here is versioned. So basically, if there's a mismatch, things won't start. They've been pretty stable, but I've added versioning to them just for the sake of, well, if there's an improvement, we should know. As long as it's not mainline stuff, I think this is the best way to go. Yes, I was expecting this question to come, and I have the right answer for this question as well. So there are a number of options for doing disassembly. You have, as I mentioned last year, you have the Intel GPU tools package, which provides basically a disassembler, a command line one disassembler. Then in the context of Mircea, because, well, they have their own assembler, they should also have their own disassembler, so you can hook up the Mircea functions. And there's also, if need be, a proprietary library that, or actually a proprietary solution that can be used, which provides a bit of a nicer output. I mean, the Intel GPU output is a bit different, but I mean, it's still valid disassembly. So the options are multiple, and there are at least 2 open source options available.
But it's not part of Linux's BFU.
No, because it's was started by the OpenGL people, and they don't have to do anything with binutils. I mean,
And regarding the challenges you listed, I think the registers are memory map. So why it is challenging?
sorry, yeah.
Oh yeah.
Well, because we might have.
We modify the memory, which will affect the contents in the register, but the GPU doesn't know.
Yeah, exactly. So, but that's a very rare occurrence. So it's mainly a corner case.
So you mentioned vectors doesn't work. Is there any particular reason, or is it just
It's not fully implemented, and the use cases where this occurs are very rare, because you're so performance oriented in the whole scenario that you actually want to avoid so-called function calls at this level. There's massive inlining taking place, because actually, while the GPU is a massive parallel entity, control flow switches aren't really that fast. So you want to avoid a bit this overload. That's
That reminds me of one thing that you mentioned that I found weird, which is the SIMD PC register. I mean, what's the difference then between SIMD PC registers and just multiple threads?
no, it's pseudo. I mean, like, it's based on the predication, basically. Oh, yeah. In the terms of, well, you disable the things, and well, the PC ends up at a certain point later where they're all unified. So there are per thread there's only one PC. Please.
Slightly a bit more about the ISA itself. How is something like single stepping implemented hardware or something like that?
Well, I mean, short answers would be look at the sources. Long answer would be this is all stuff that's in the open source tarball, so I can freely speak about it. There's a so-called system routine that's being used by the GPU to do context switch, context save and restore. For you familiar with the Intel Intel x86 architecture, the Xsave buffer, right? This is called, well, a debug surface in this scenario, and there's a very simple protocol which is being followed by this system routine that allows you to do single stepping. So, well, this system routine takes care of it if you feed certain registers with certain values. So it's a very simple protocol, and it works very well and does exactly what it's expected to do. Any other questions?
What's your GDP version? Did you upgrade it?
No, not yet. I have it as a work in progress, but
7.6?
yeah, it's still the one that's part of this product is a 7.6 one. Yeah. Any other questions? Okay then. Thank you for your attention. That will be it.